Okay. Okay. Hello, everyone. I hope you all had a great day so far. Uh, Continuing our discussion about the inverters and how we could categorize the inverters, we were over the concept of the grid forming inverters. We mentioned some differences between the grid forming and the previous category, grid following, that we described in uh, previous sessions. And we kind of like talk about, okay, why we need grid forming, how it works, what are the main differences, what kind of control methodology we are going to use in grid forming uh, instead of all those methods that we used in grid following. And we mentioned that the main control strategy that grid forming inverter would adopt for controlling their output and basically supplying enough active power and reactive power to answer the load at their terminals is the Droop control. Okay, let me see what is the chat. Hey guys, do you hear my voice? I don't think I'm mute, but I might have a problem with my computer. Anyone? Okay, so okay, so okay, you might. I'm not sure because I can't see the name of the person who had problem, but other people seems to don't have that problem. So yeah, you might check your yeah setting. Thank you. Okay, let's continue. We said that the main control methodology that we use in grid forming inverter is named Droop control. But where that Droop control came from, like what is the definition of Droop control? As the similar that or this similar to the discussion that we had about the grid following, when we put our focus on a control system, because that's one actually like drive the switches. Here we are going to do the same. So we are going to go a little bit deeper to the Droop control methodology and see what's going on inside this Droop control methodology and get more familiar to understand how to design the control and how to implement it for the inverter-based resources, both single phase and three phase. Okay. I wanted to let you know the most of the examples you might find on internet, either on like the videos or like the text, they are mostly trying to like apply the group control into a three-phase system because it is more convenient. Like the low power single phase inverter are normally not uh, designed to grid as a grid forming inverter. They are mostly low power, so they are mostly grid following inverters. So most of the grid forming inverters basically are gonna be at three phase kind of like settings. That's why you would see most of the resources on internet for a three phase inverter. But as you know, it's not kind of like that difficult to like connect these two concepts because those three-phase systems are basically just an extension of what you had as a single-phase system. Okay. Now, with that being said, let's dive to the uh, Droop control and see what is a Droop control is. Okay. The definition of the Droop control is that it is a decentralized control strategy, okay, that we use normally in power system to regulate the active power and reactive power injection at the output. Okay. Now, where that Droop control system came from? What is the origin of that solution, that technique? in the synchronous machine, or basically the rotary machine, not just synchronous, the rotary machine, when they want to control the speed of the machine in their field based on the output power that they have to provide, that mechanical power that they have to provide, okay? Normally they use a speed regulator, okay, and use the control of the rotational speed of that rotary machine, okay, in order to control or dictate how much power or how much torque they would provide at the mechanical part at the output of their machine. That control tries to like mimic, tries to balance the electrical power that is injected into the system and the mechanical power at the output. And if they are not balanced, there is going to be an increase or decrease in the speed of the rotary machine. Okay, if the mechanical load is more than electrical load, the speed is going to decrease. If we have less mechanical load than the power that we are injecting to the rotary machine, our speed is going to be increased. So the droop controls comes from that idea of, okay, we want to droop our speed, okay, based on our uh, input and output power to balance our system and keep the speed at a constant margin, as a very specific margin of our desired, rotational speed. Is that clear? What we said. Now we are going to go over the math, like the equation of that, and you're going to see how it works, but it's just like an introduction to that idea. So what they're doing for grid forming, they actually borrowing the same control strategy that they use for rotary machine in order to make the inverters work as a grid forming inverters instead of grid following inverters. Now, why droop control is important? The first thing that come to we have to like note is that the droop controls are decentralized control. Okay, when we say decentralized control, it basically means is another way to say they don't rely on the grid. Okay, because grid following always follow the grid. So every inverters that connected to the every grid following inverter that connected to the grid, they have to match themselves with the frequency of the grid as a central entity. So basically, eventually, if you zoom out, all their control system are basically centralized control system because they are getting dictated by one entity. Okay. Now, in Droop control, we wanted to like have a decentralized kind of like control system is another way to say we don't rely on the grid. We are going to work as an independent entity in the system. Make sense? So they are decentralized. They will enhance the stability of system. We already talked about that. How they enhance the stability of the system based on the fact that they are not depending on the grid. And if we have an unstable situation in the grid, they would not, grid forming would not be affected, and they basically try actually to help stabilizing the grid based on their kind of like capability, okay, the range of their capability. You have a question?
Yes. So when you say decentralized control, I'm assuming that means it's not directly affected, like making it move by the system, but it's still affected by the system because otherwise how would it know what the ratio is to keep, right?
Two things. That's not defined. The ratios and the frequency are not defined by the system. So that's why it's decentralized. So the main parameters are defined based on the each inverter's control system independently. Okay, what is getting like I think what let me see if I understand your question. Consider that you are an independent person, okay, and I'm an independent person, okay. Both of us work as based on our own rules and regulations, okay. But for example, if we some like for example, if we see a problem in the community, okay, both of us the rules are different, but we are gonna help solve that problem. Either we share the load or someone would pick it up. So no one mandated me or you to pick the load. Okay, you respond based on your rules and regulation that you have in mind. Now let's translate it to the grid system. You have a grid system. Okay, you have a network, you have an inverter, a GFM, grid forming inverter here, connected to a network, and another GFM maybe here. Okay, now this is your network, the power network. Okay, the control system here would has its own rules and regulations. So we would dictate, okay, the dictation is that I want frequency at a specific value, like 60 hertz. I want voltage to be like at a specific value, like 110 or like 240. Okay, so it's defined in the system. Same goes here. Okay, now in the network, if something happens, like let's say there is a decrease in the load or increase in the load, which makes the deviation of the voltage or frequency at the terminals of the GFM. Now, GFM, because it has its rules and regulation, and it says, okay, I do not tolerate that increase or decrease in frequency and voltage. I will answer that and I will solve it. Yeah. So it sees the deviation. Yes. Exactly. Before in the grid following, it was the grid that would force grid following to answer my need. Now it's the reaction to the already existing need because GFM control system wanted to keep up with its specific mandated settings. Now, if you have enough GFM, okay, and there is an increase of like a load, okay, both of them would see that and start responding. And when this one responds, the deviation would decrease a little bit. So this one has a little as lower load to bear. So it's basically without any communication, they start sharing the problem. You know what I'm saying?
Question. Are all of the Droop controls centralized?
No. All the GFM are decentralized. As that's the actually that's the
No Droop.
the premises of the grid forming. Droop control is used for GFM or synchronous machine. They are based on strict settings. So they wanted to keep the frequency or the level of voltage or the speed of voltage machine at a certain level. So they do not connect to any centralized or any other inverters or like any other controllers, okay, to see what should be the settings. They have their settings, okay, and they only follow that settings.
Right.
So independently. So yeah. Now, with that being said, I don't want you to look at when I say GFM or like grid following inverter, I don't want you to like visualize it as a very strict, like, okay, I have one inverter, like physically, I have one inverter that is GFM. Okay, no, that's not the case. It could be a group of inverters connected together, okay, and work as a GFM.
What usually.
Usually is, yeah. And similar to the concept of the multi-level inverter. In multi-level inverters, you had several edge bridge that work together to act as a single multi-level inverter. Okay, so in GFM also, you would have several inverters that work together to create a overall general kind of like GFM that answers the grid. If you have a group of inverters, now they cannot be, all of them cannot be dictating the control system. If they are work together as a group, one would be the master, and the other inverters that are connected to that group would work as a slave. So one control system would dictate the whole situation. Is that clear how it works? So this is kind of like the situation. Were there any question uh, between the guys in the Zoom meeting? No? Okay. Now, as we talked about like when I wanted to answer the Christine's question, another aspect of the group control is the power sharing. So because they all want to keep their own settings at the terminal, they basically motivated, kind of like they are, to pick up the overload or the underload situation in the grid. So without any communication with each other, they basically share whatever deviation happens in the grid to get rid of that deviation and stabilize the system again. So there is no communication between these two inverters in the screen. But since both of them sees, like for example, an increase in the load, they both try to answer that. Eventually, it means that they share the load, and how would be kind of like divided between the two? Based on their own capacity. So if this inverter has higher capacity, it would answer faster to the increase of the load. So the lower capacity inverter, okay, would end up with a less deviation to address. Is that clear how it works?
So that you not once.
Yeah, they both want to fix the frequency at, like, for example, 60 hertz. If anything happened in the grid that jeopardized that for them, they would force the frequency to like go up or go down to that 60 hertz. Now that means either they have to like inject more power, more active power, or lower their injection of the active power to regulate that frequency at the point that they want. Same goes for the reactive power. We said reactive power answers to the amplitude of the voltage. So they have a setting for amplitude of the voltage. They do not tolerate deviation. If anything happened that jeopardized that setting, they would force injecting a reactive power or consuming a reactive power to address that deviation. Make sense? Now, and the other part is the seamless integration because they don't have to synchronize with the grid. Okay, it's like a plug and play kind of like situation. They work independently, so they just have to like connect it to the grid, and they would catch up. They don't need a synchronization period to get synchronized like grid following, to get synchronized what are the situation in the grid and how I can be, what can I have our settings. You know, in the grid forming, if you remember, we talked about in a PID system, we talked about the Ziegler-Nicholas method that would help us to tune our initial values for PID control. Remember that? So basically means grid following needs a transition period from zero to when they could reliably connect to the grid. Okay, from the initial value to the optimum value of their control system. That's not the case in the grid forming. They are set it before they start working. So they connect and they start working. Are we good? Now, as we said, this basically the idea of the droop control comes from the speed control in a rotary machine. Okay, in rotary machine, if you have an increase of a mechanical load in respect to injected electrical power, okay, the speed would go down. It's overloaded. So the AV or uh, the speed controller in the rotary machine would try to catch up by injecting more electrical power, so it would compensate the speed and keep the speed at a certain level. Okay, so basically, like this is the graph. This is the graph that describes the frequency or like the speed of the rotary machine and the amount of the power that you inject or basically the difference of the mechanical power and electrical power. Okay, if you have more mechanical power than electrical power, you're moving toward the uh, right side of the axis of the power. Okay, so it makes the frequency go lower. So the droop control would force the point, the point that you are back to the lower amplitudes. So it would keep the frequency to compensate the frequency at the level that it wants. Make sense? This is kind of like the situation. Now, this slope shows how good the response of the droop control could be, how fast it would respond, and how stable and like there is like with a less overshoot and undershoot, it would respond to the system. We are gonna again talk about that a little bit when we talk about the actual droop control in inverters. Any questions so far? Go ahead.
I did some research on that. And I know you sound good, but I'm curious, I was wondering if you knew like the exact ratios that are like, if there's a standard, because I have for a 4 to 5% change in power, it's about a 1% change in frequency.
There is it's not a solid kind of
I
like
know it's
yeah,
solid.
but there is a like a survey run in the GFMs that already exist and like based on their design and their capability and the capacity of the power that they could provide, all those. And also depends on the grid that they are connected to. So everything is like there's a several parameter that would affect that. But there is a survey, there's several surveys actually run by the different utility owners and and like the federal agencies or like the government kind of like in different countries that they kind of like define a specific margin so the manufacturer could have an initial kind of like setting. Okay, but
Yeah.
eventually it's the utility owners responsibility to analyze, to model the system with that inverter, analyze how it should set the settings, the amplitude in the control system. Okay, so it could answer perfectly within the margin of the standard without too much deviation or without a kind of like a long wait for the response to the deviations. Okay, so proper settings based on the actual grid that the inverter is connecting. So now this is actually a very good point because I wanted to like mention in a parenthesis one of the biggest regulation rules that exist, and this is one of the one of the rules that prevent increase of the renewable energies. If you want to add any resources to the grid, you have to run a full analysis over the grid, transient power flow, everything, reliability, stability, full analysis on the grid of how would be that resource would change the dynamic of the grid and how it would affect other utility owners.
Yeah, learned about that.
Yeah. So, and this is not an easy task. Like it would take years to do that, you know. So if you wanted to like add a solar power plant to the grid, it's not like a construction kind of like project. The simulation project takes years to get completed. Okay, so yeah. Okay. What? Okay. Now,
So,
yeah,
oh, sorry.
yeah.
And then but there's a regulation on that as far as like from IEEE. saying-
The regulation is how much deviation you allow to happen Okay, for the frequency and voltage. Okay,
Like,
and yeah, so there is a margin like frequency is 0.1. Yeah, frequency is the margin that the grid demands. You cannot have more than 0.1 hertz change in a frequency. Okay, that's not allowed. Voltage also have a variation margin. Okay, that margin is standard, and also they have a standard of how fast you have to answer to the grid. So you can't, like the inverter cannot wait for like a day to see what's going to happen. There is a margin of the time. Okay, you have, yeah. Also, you cannot answer faster than a certain margin because some transient are not supposed to be addressed. They are temporary and they will fix by themselves. So if the inverter wanted to like address everything, it's gonna have like actually it is increased instability because it change all the time. Okay, so this is the kind of like the rules of immersion, but based on those rules, you set the settings on your parameters. Now, in group controls, and basically in the inverters, we have two loop of loop controls in our control system, general control system. One would act on frequency, another one would act on voltage, because we said grid forming want to dictate, mandate, stabilize, whatever you want us to like look at it, okay, the frequency and the amplitude of the voltage at their output. Okay, they want to shape the stable grid, which means stable frequency and a stable level of voltage. Okay, now so we have two basically function in our control system. One acting as a frequency group, another one as a voltage group. Now we talk about that briefly, and we are going to talk about that after the midterm in more deeper kind of like conversation. We said that the active power normally relate to the phase. Before we said is the phase angle. Okay. Now I wanted to like give you another interpretation of the phase, okay, and the difference in the phase angle. We had a sinusoidal voltage, a sine of omega t plus theta. Okay. If I add a delta theta here, there is two ways to see that. Either I change the initial phase angle, or I could translate it to a delta omega t. Makes sense? I could either force that delta t into that theta, or translate it to the change in the frequency and force it to that term omega t. Is that clear? What I mean? No. Before in grid following, we would see this delta t at our terminal and would translate it to the initial phase angle. In Droop control, because we want to like react to the certain frequency, we would translate that differentiation, that deviation, into the deviation in the frequency. And we translate that phase difference into a frequency difference times the time. Are we good? Now, if we do that, we could use the same concept that we learned, that the active power, the amount of active power that flows from one point to another point, okay, it relates directly based on the amount of phase difference between the 2 points. Now, when we translate it to the frequency, means it depends on the difference between the frequency of the 2 points. Are we good? Do you have any question?
So you said the phase, because I thought phase was Q. Like when you have too much inductance and it makes the current out of the lead.
No, that's something different.
Oh,
Q makes not Q. The inductance and capacitance create phase shift between voltage and current. That's one idea. That's one concept. Now, reactive power, okay, there is a power flow formula.
So Q, right?
No.
Reactive.
Reactive power is Q, active power is P. Okay, so in power flow formula, search on power flow formula is basically a function of the the active power is the function of the voltages, voltage I, voltage K between the node J and K, and the delta theta I JK. Okay, and Q is a function of uh, voltage J, voltage K, and also the delta theta of JK. Now, if you look at the functions, okay, the effect of the voltages, okay, over the dynamic of P is negligible. You can neglect that. Regard to effect of the phase difference on the behavior of the P, on the dynamic of the P. So these two values, the deviation in these two values has much less influence over the deviation of the active power flow compared to the phase angle. Q is reverse. The deviation in a phase angle has much less effect on the dynamic of the Q rather than deviation of these two voltages.
Oh, okay.
Okay? Yeah. So you can basically interpret the need of active load by quantifying it with a phase difference. Does that make sense? Yeah. Okay. So now in Droop control, we translate that phase difference into a frequency difference because they are basically the same. They are radians. Okay. We just wanted to like make a mathematical transformation. Okay. They would be, but the problem is that because like in grid forming, you see this omega naught. This omega naught is set within the control system. In grid following, we don't have that omega naught. We have to read the grid. So this on that part, both of the terms are basically varying on the terminal. You don't have a solid set point if you wanted to like transfer it to the frequency. Is it clear? So now that we transfer the translate or that phase difference into a frequency difference, now we could relate the difference or the deviation in active power, okay, into the deviation in the frequency. So we measure a frequency, we measure our active power, we have a set points for both of them decided in the control system. Now, if there is a deviation, we are gonna eliminate that difference. Make sense? Like a PI controller. Is that clear? Same goes for the voltage control. It works with the Q again. We have a set point for our values based on the standards and regulations. Okay. Now, if there is a deviation in the grid, we are gonna pick that problem and like address that problem and make the voltage equal to V0. Is that clear? So there is a deviation in the voltage. You observe the deviation in the voltage. You add the Q, okay, or decrease the Q and cancel out that deviation. So again, V equal to V0. Same goes for the P. Make sense? It's like a feedback control. This M and N would define a slope of that line that we see before in the rotary machine. Do you remember that? This line? The line that defines like the frequency and P or like the V and Q is the same. The slope is the M and N in this formula. So if the slope is kind of like steep, okay, that means we have a smaller frequency and voltage deviation, okay. But if the slope is kind of like a flat line, okay, that means we improve the response speed, it would act faster, but then the deviation would be bigger. A slope you have to change. Yeah, you have to set that. As a designer, you have to set the slope based on the regulation that you have. So for example, the standard would say, okay, you want to have you want to limit this frequency and voltage deviation to a certain level. Plus, you want to limit the response speed to a certain margin. Now, what is the optimum value for M and M that you can provide both conditions? Those are provided by standards, but when you wanted to like set that, okay, it's not like, okay, we have this standard. It says like a speed is like from 1 to 2 seconds, and the variation is like 0.1 for frequency or 1 volt, one delta V for voltage deviation, and based on that, because this is a solid frequent standard, okay, every grid forming inverter based on these values would have like a M equal to 2 and N equal to 1. No, that's not the case, because this is also relates to the grid that you are working with. You have to simulate what's going to happen when your inverter reacts to the network that is connected to. And while limiting these values, it would define its own specific M and N. Make sense? So it's kind of like a optimization kind of like process. In phasor domain, yes. In power we use phasor domain. So normally we talk about RMS when we talk about the value, unless otherwise told. Like always the values are RMS unless it's mentioned that is not. Uh, any question so far? No? Okay. Now, when you want to design a Droop control, okay, to provide such a response to the deviation of the voltage and frequency and stabilize, like, the output of the inverters in grid forming, there are several key parameters that you have to like keep in mind. The most important one is that M and N, those Droop coefficients. As we said, they have to like be determined by how strongly we would respond to the change in the network that we are connected. And strongly means both time and the overshoot or undershoot, the variations of the control system. Okay. Next time is operating set point. You have a standards and a regulation for active power, reactive power, voltage, and frequency. So we have to know what are the set points are based on the level of the voltage, and like, if you wanted to like connect to the low voltage network, medium voltage network, or a high voltage network, is it gonna be in the transmission kind of like setting? It's gonna be a microgrid. It's not gonna be connected to the actual grid. All those things would change the setting. Okay, they are in the standards. Okay, so you don't need to like figure out those settings. They are in the standards, but you have to know which one would apply to your situation. Okay, so choosing the appropriate settings is the next thing that you have to have in mind when you want to like work in that. The third one is, as always, because we rely on measurement, that means we have errors, noise, interference. So that means what you read as P here, or as Q here, or V and omega here, okay, is not going to be error free. So you have to filter the noise in order to avoid misguiding your control system. Make sense? always we have a simple low pass filter in the power system to mitigate the noise. Now, this is not all that happens. You want to measure the grid situation, okay, and you want to address that. But when you want to inject a reactive power or active power, it's not that you like the grid is someone here and you hand the active power or reactive power to that. There is a transmission line, okay, a transmission system that transfer your injected power to the consumers or to the grid, to the point of common coupling that you need to like basically the delivery point of that active or reactive power is. Okay. Now, what is that transmission line? It's resistance, inductance, from electrical perspective, and a little bit of capacitance. So if there is a resistance, what that means? That means that transmission line would have a power consumption, a power loss, active power loss. So you have to count it. Otherwise, what you deliver is not what the grid needs. Same goes for the reactive power. It has an inductance and a little bit of capacitance. That means it either mostly consume or in very rare cases generate some reactive power. Okay, so you have to count on that. That brings out a virtual impedance kind of like control system model. You could search on that. Okay, but this is another point that you have to have in mind when you are setting your control system. Are we good? Any question about that? Sorry? This is the part that is one of the part that I said, like each controller based on the network that it connects to, you have to set M and N accordingly. So it's not a solid M and N. Any situation, any network has different setting. Okay, this happens to that. So like that virtual impedance, okay, basically tell you, okay, what is gonna be the configuration of the network and what is gonna be the losses from your terminal to the point of common coupling when you deliver the power to the grid. So all of that is within that simulation. Did I answer your question? Okay. Now, when you want to implement the Droop control inverters, okay, what you have to do, the parts of the Droop control inverters, okay, could be divided in 4 categories, 4 group, 4 boxes, okay? One is the measurement. So basically, what you measure, as our formula showed, is active and reactive power of the grid at the terminal. That means you have to measure the voltage and the current of the terminal. If you measure the voltage and the current of the terminal, then you can calculate the P and Q of the grid. Okay? If you have the P and Q of the grid, you can calculate the frequency and the voltage responsible by that P and Q. So now you have your measured values. Okay? Now your Droop control, that formula kicks in. You have a setting of omega 0 for like frequency, and you have a P that defines what should be the omega to eliminate that deviation between the set point P naught and P, actual measured P. Based on that formula, you would find the omega that you need, okay, to eliminate that deviation in the P. You took that omega, same goes for the E. Active power, E here means the voltage, okay? And you would set the we calculate the reactive power, and based on the Droop control, you would calculate the voltage needed for eliminating that deviation in and reactive power. And when you have these omega and E from this frequency, this omega and this V, now you could calculate, okay, how much active power I have to how much increase or decrease in active power I have to do in my inverter, or how much increase or decrease in reactive power I have to do in my inverters to meet that change. Is that clear? After you uh, generated that values, now you convert those reference values to the PWM. You would give that to your PWM and it would react accordingly. Now, one thing that we mentioned, and you might heard or like read on the internet, is that normally they consider grid following inverters as a current source and grid forming inverters as a voltage source. Okay, it's not a very kind of like good way, to be honest, to like represent these, but I want to like explain why they doing that. Okay, they they kind of represent grid forming inverters as a voltage source because they try to stabilize the amplitude and frequency of the voltage. So they basically that the output of their value, you would have the the function the function for your voltage, because our Droop control is setting the voltage and the frequency. Are we good? So that's why they consider the grid forming inverters as a voltage source kind of like system. The key differences, as we mentioned, is the decentralized system and not relying on a grid, meaning we don't have a PLL to find out what the frequency is. We set the frequency in GFM. And because they mandate or like they set the rules for the grid or the output, GFM are capable of running a microgrid, meaning when we don't have a strong grid to stabilize frequency and the level of voltage, GFM would stand up and like solve that problem for you in a microgrid. Okay, we already talked about that. You don't need to like repeat that. And also we already talked about that. It's kind of like when multiple GFM works together. We already in the beginning of the discussion mentioned that they are basically coordinate because of the way they respond to the deviations. They basically coordinate without the communication. All they see is there is a problem in the grid, and all of them stand up to solve that problem. Now, some has more capability, so it answer faster and bigger. That means there's less leftover problem for the low capacity GFM. So power sharing is a kind of like an intrinsic kind of like behavior in a Droop control and in GFM. Okay, because of their formula, because the Droop controls comes from the rotary machine mechanical kind of like formulas and control system. They are inspired by that. So the behavior of the GFM mimics very similarly to the traditional resources. So it's more understandable for, the grid analysis software. And since all of them are connected to grid mandating a certain frequency and voltage, they would always find a natural equilibrium uh, in order to address all deviation. Does that make sense? Are we clear on that? Any question so far? Now, I put a step by step guideline for how you can implement the Droop control in MATLAB Simulink in my PowerPoint. Okay, so it's a step by step, like putting the measurement of active power and reactive power. The next step is implementing the Droop control. So we are going to transfer that measurement into what signal that we want, the voltage and frequency that we want to like stabilize, and then apply the voltage Droop and frequency Droop to make sure that okay, how we should address that deviations. And at the last level, we generate the frequency and voltage for PWM based on the result of our Droop control. Are we good? Also, come on. Also, I added a video that shows exactly like it explained the Droop control and shows an example of uh, developing a Droop control in a MATLAB Simulink. Okay, so that could be a very good kind of like again source for you to like have a better understanding over what's happening. That being said, I uploaded several videos, including this one, okay, on page in our course page on Canvas. Okay, go through those. Two of them, or like I think, yeah, two of them are basically seminars or webinars that a scientist or like a scholar would explain their achievement on the grid forming and their definition of the grid forming and how the Droop control works. It's very good and informative kind of. I know it's a little bit longer videos because it's like I think more than 30 minutes. One of them are 50 minutes around, like something like that. I know it's long, but it's worth watching. Okay, so it would gives you a very better understanding on what's happening in grid forming and what's happening in Droop control. Okay, now I uh, posted also an assignment, a reading assignment, basically. Okay. We all said that we have grid following. They cannot work independently. Weak grid scenario would have an instability situation. Now we want to solve the grid with the grid forming inverters. We're gonna introduce synthetic or like virtual inertia. We are gonna solve the problem. Okay. These are standards understanding. Okay. To be honest with you, I do not believe that grid forming is answer to those problems. Okay, now I posted an assignment on the uh, Canvas, a reading assignment. There is a paper that explains the duality between grid forming and grid following. I don't want to bias your mind. Okay, that's a very good paper because it's uh, discuss the grid forming and grid following from the like a engineering perspective, mathematical perspective, control system, simulation, and all. Again, it has a multi kind of like viewpoints over that the two categories. Okay, I want you to read that paper. Okay, and try to summarize your understanding, not the paper, your understanding about what it discussed, what it's been discussed in that paper, maximum one page. So you don't need to like prepare a long kind of like review, maximum one page of your understanding of that paper. Are we good? Any question? No? Okay, so that's it for today. And as I mentioned before, next week we are not going to have a lecture. You have the next week to work on your midterm assignment. So use that time to work on that. I am going to be in my office. If you need me, if you have any question, if you need help, email me or set an office hour. Okay, we could work together. So do not hesitate to contact me, and please do not postpone it to the last minute. Okay. My goal is for you to like finish your all the assignment for the midterm before the breaks starts, so you could have a kind of like a free mind on the breaks. Okay. So that's it. And if there is no question, we could finish this session. No? Okay. Have a good day and thank you.